Hi, and welcome to our webinar, Advanced CO2 Consequence Modeling for Safe CCS.
Firstly, let's look at CCS, carbon capture and storage, in brief. CCS is viewed globally as an important key carbon abatement technology. How does CCS work? Well, the capture generally takes place at large stationary sources of CO2 emissions like power plants or industrial plants that make cement, steel, and chemicals. The captured gas is then compressed so it becomes liquid-like and transported to a storage site, generally through a pipeline. Once at the storage site, the CO2 is pumped more than 800 meters down into geological formations like used-up oil and gas reservoirs. The schematic on the right here shows the operational and planned future capture capacity of CO2. Now, there are already around 40 commercial CCS facilities in operation, but over 500 CCS projects are in various stages of development across the CCS value chain. And by 2030, we have an estimated annual capture capacity of more than 300 million tons of CO2. So it's quite clear that the safe handling of CO2 will become increasingly more important as we build out the CCS value chain and technology. Let me then talk a little bit about some of the key properties of carbon dioxide when it comes to safety. CO2 is a colorless, odorless, and invisible gas at standard conditions. It's heavier than air, it's not reactive, it's not flammable. CO2 can exist in 4 phases: gas, liquid, solid, and the supercritical phase. These phases can also be seen in the phase diagram on the right, where you've got a temperature on the horizontal axis, pressure on the vertical axis. So depending on the pressure and temperature of CO2, you can be in the gas phase, solid phase, liquid phase, or the supercritical phase. You often hear the term dense phase when we talk about CO2 and CCS. Dense phase is not a phase per se, but it refers to high density CO2, namely when the CO2 is either liquid or supercritical. Now, at atmospheric pressure, CO2 can exist only as a gas or in the solid phase. The reason for this is that the triple point pressure of CO2 is actually above atmospheric pressure at 15.18 bars. Solid CO2 is also known as dry ice, and at atmospheric pressure has a temperature of minus 78 degrees Celsius. Supercritical CO2 has viscosity similar to that of a gas, but density similar to that of a liquid. And finally, I'll mention that when CO2 dissolves in water, it forms carbonic acid. Having talked about some of the key properties of CO2, what are the hazards we should be aware of? Well, here I've grouped hazards into 4 different categories. The first category I've called people impact. Now, CO2 is an asphyxiant when displacing the oxygen in air. This is particularly relevant if there is a CO2 release in an enclosed area. But CO2 is also a toxic material in its own right, and at higher concentrations, it can have toxicological impact with a threat to life, at concentration of 50%, for example. Second category I've called cryogenic impact. Now, cryogenic impact is basically something you see when you have CO2 stored at high pressure and it undergoes an expansion. You get high velocity, low temperature, and you get an equilibrium of solid and vapor CO2. So you get a 2-phase jet of CO2. Now, any personnel exposed to such a cold jet of CO2 gas can suffer cold burns and frostbite, and anybody inhaling that kind of a low temperature 2-phase jet of CO2 can get severe lung damage. Thirdly, we have a category here called the environmental impact. Now, that environmental impact really depends on a lot of location-specific factors. But in general, we can say that animals, just like human beings, may suffer hypocapnia and asphyxiation. CO2 dissolves to form carbonic acid and absorbed in soil. It can cause vegetation die-off. But finally, there are some other hazards as well that's worth mentioning that don't belong to any of the other categories. So I've sort of just grouped them in a generic other hazards category here. And one of them is reduced visibility within a CO2 water vapor cloud. Due to the low temperature of the cloud, water will condense in the air and visibility can be greatly reduced. That can make it difficult for people to navigate if they have to escape. If a CO2 cloud with reduced visibility goes over a road, it could be problematic for people in cars on roads. Another thing to be aware of is that when the CO2 concentrations in the air is below a certain threshold, the internal combustion engines may get trouble working and you can have your engine stalling. So again, if you have a road being affected by a CO2 cloud, that could cause vehicles to stop. And finally, like any pressurized containment, if the containment fails for whatever reason, then projectiles can be flung from the containment failure, and that could cause a danger to personnel nearby as well. Right. Okay, so that were some of the hazards we should be aware of related to CO2. But where can those hazards occur? Well, there is a nice schematic figure here of the CCS value chain. This image here is provided by the Global CCS Institute. And it sort of shows from the CO2 capture stage, where you may have pressure vessels with high pressure CO2, you may have compressor action. And of course, if you have an accidental leak here, you need to be able to monitor releases from those kind of containments. Then the CO2 is transported away from the capture plants in pipelines. It could be buried, it could be above ground, and it may be transported to a buffer storage where it's temporarily stored before being transported offshore, again in pipelines, which then will go under the sea, out to the CO2 injection site, where it will be put down to geological storage. So to do a proper assessment of hazards, you should really consider potential for releases anywhere along this CCS value chain. Now in DNV, we have software tools Phast and KFX that can help you with your hazard analysis in the CCS value chain, which is what we will be talking about in this webinar. Firstly, let's look at CO2 releases to the atmosphere. My colleague Marion will later on talk about CO2 release underwater, but for now, we talk about releases to the atmosphere. And before we talk about how we can model that, I just wanted to show a couple of videos of controlled releases of CO2 to the atmosphere. So these are experiments carried out at the DNV Spade Adam facility about 10 years ago as part of the CO2 pipe trans releases. So what you're going to see here is CO2 stored at around 100 bar, about 10 to 12 degrees Celsius. So it's dense liquid CO2 release through a 100mm orifice. What you're looking at towards the release points, you will have a CO2 cloud coming towards you as you're looking at the release. So what you will see is that you have a high pressure release, high velocity release, and the CO2 will come towards you, towards the camera. You can see the water vapor in the CO2 cloud, and eventually you lose all visibility due to being engulfed by the cloud. So this hopefully illustrates what can happen if you have a CO2 cloud impacting you. Now, there's another view of the same cloud or same release really, but from a different camera angle. So what we're looking at here is the same release, but from behind. And this is actually a time-lapse video, so it will go in high speed, but you'll see how the release goes away from the camera in this instance. You see a high pressure release, it's a horizontal release, and the release is cut off. You see how the cloud has drifted off in the background. And again, you see very clearly a visible cloud here of CO2. Now, actually, this is a two-phase release. So what comes out into the atmosphere is CO2 gas and also solid CO2 particles. The solid CO2 particles, as they mixes in with air, will sublime into CO2 gas as it moves away from the release point. Now, Phast consequence modeling. How can we use Phast to analyze CO2 hazards for releases to the atmosphere? Well, Phast has, as a consequence modeling tool, a history of more than 40 years. It's used worldwide in a variety of industries by more than 1,000 companies these days. And just to give you a schematic overview, in Phast, you start by defining your loss of containment scenario. What is your material, pressure and temperature, and the scenario you're trying to model. Phast then calculates the discharge, how much material is coming into the atmosphere, how quickly is it coming into the atmosphere, and those results are then being input to the dispersion model in Phast. The dispersion model then takes the weather conditions that you have specified into account and calculate how the released material spreads in the atmosphere. It calculates concentrations at different locations. After that, we calculate the effects. So for a toxic material like CO2, you look at the toxic effects it may have on people at any location around the release site. If the material is flammable, then radiation and explosion effects are also taken into account. Specifically for CO2, though, we look at what release scenarios are covered. We talked about CCS capture. You may have storage vessels, right? Well, for those pressure vessels, we can model leaks in Phast. We can also model the catastrophic rupture where the whole containment fails. We also talked about how CO2 is transported in pipelines. You can model long pipelines buried or above ground, punctures or full-bore ruptures of those pipelines. Following the discharge, we looked at some video earlier. Here you have a still photo of the same release that we saw earlier, where the dispersion is calculated by what we call the unified dispersion model in Phast, which takes into account a variety of effects, including the heavy gas spreading of a gas like CO2. And finally, the toxic effects. Based on the concentrations from the dispersion model, we can use probit values, which relates to the toxic properties of CO2, to calculate lethality levels. So you can basically get contours like you see here in the middle bottom picture, which basically shows the probability of death contours for CO2. Now, I talked earlier about some important properties of CO2 and how at atmospheric conditions, CO2 is either a vapor or a solid. So more than 15 years ago now, we made some extension for Phast so that we can handle solid CO2, because Phast in general handles liquids and gases. But for CO2, we made some specific extensions so we can handle the important features of solid CO2 as well. On the discharge side, we account for solids from the expansion from the pipe exit or from the leak orifice down to atmospheric pressure. And in the dispersion, when we have a two-phase release, we have a vapor solid equilibrium of CO2, and we take into account the appropriate thermodynamics for sublimation of solid CO2 particles in the cloud. Note though that no deposition of solid CO2 on the ground is modeled. That is viewed as a conservative approach, because when we keep the solid CO2 in the cloud, it will cause further sublimation and cooling, keeping the gas cloud heavier. What I just said can also be summed up in the picture on the right here, whereas the schematic shows that in red, we see what happens within the containment, in the vessel, inside the pipe. We don't do solid CO2 modeling and solid CO2 formation, but as soon as the CO2 enters the atmosphere, we do take into account the appropriate solid properties of CO2 so that we get the correct thermodynamics, which is really important to get the correct density of the dispersing cloud and the right cloud behavior of CO2 when it's dispersing. Right, I hope you're still with me. I have now made several claims about the capabilities of Phast for CO2 modeling, but how do we really know that Phast models CO2 releases accurately? How do we know that we can trust results that comes out of Phast? Well, one of the key activities that we do in the model development in Phast is to compare Phast predictions with experimental results when experimental data is available. At DNV Spade Adam Research and Test Facility in the north of England, they have carried out a number of CO2 releases over the years. And we have carried out comparison of both Phast discharge and Phast dispersion against these experiments, which has helped us over the years to assess our models and also make improvements to our models. There's a list here of various experiments. They include dense releases, supercritical releases of CO2, orifice type releases, long pipe releases, and also buried pipeline releases. I will come back to some of these experiments in more detail later. Now, circling back to the schematic we saw of the CCS value chain earlier, one of the things that strike me looking at this diagram here is that there's a lot of transportation pipelines here, right? Big part of the CCS value chain involves transporting CO2, be it onshore in pipelines or indeed offshore as well. So pipelines are important. Assessing hazards from pipeline releases is clearly crucial when you want to understand safety of your CO2 operations. Now, the CO2 pipeline modeling in Phast is quite extensive. We can handle all fluid phases from liquids, vapor, and supercritical CO2. We have full bore ruptures. We have partial breaches and small holes of a long pipe. The modeling is transient, so we account for the pressure decay over time. You can see how the flow rate decreases over time as the pressure decays. You can specify valve action so that you can isolate your CO2 inventory upon leak detection, and you can see the impact of that for realistic modeling. And you can specify a finite pump throughput of CO2 in your pipelines. I'd like to mention that subsea pipeline releases is not explicitly modeled in Phast, but if you're interested in subsea pipeline releases, then please stay with us, and Marion will talk more about that later on in this webinar. For onshore pipelines, Phast can model buried pipelines, and for buried pipelines, if you have a release, crater effects are important, and we'll have a closer look at that now. So if the pipeline is buried, one of the key things to specify is what is the depth of soil? How much soil do you have above? What's the soil cover above your pipeline? And what type of soil do you have? So those are key inputs to modeling the buried pipeline. The model then calculates the dimensions of a crater, and you get a modified velocity, you get air entrainment, and you get the appropriate solid CO2 fraction. The picture on the bottom left here is again from some experiments from Spade Adam about 10 years ago. They were carried out as well. It's the COSHER experiments, where high pressure, dense phase CO2 was released as a buried pipeline release. You can see the crater formation here. So one of the key things here is to get the dispersion modeling in a crater release correct as well. On the top right here is an aerial view from the COSHER experiments, where CO2 you can see has spread almost as a gas blanket in all directions. And this stalling plume or gas blanket effect was also something we included in an improved modeling of buried CO2 pipeline releases in Phast 8.9. So that was released in June last year. And the COSHER experiments guided us in this development. And you see the schematic here and how Phast is doing this. First, we have almost this kind of instantaneous cloud behavior. And as the pressure drops and the flow decreases, the wind effects become more important and the instantaneous cloud starts drifting away. Now we compared the predictions from Phast for these COSHER tests against the actual concentrations observed in the experiments. And I'm going to show you a couple of plots from that here. So if we look at the plot on the left, that's the first of the two COSHER tests where the wind was around 4.7 meters per second. In this plot, we've got the observed concentration in the experiment on the horizontal axis and the predicted concentration from Phast on the vertical axis. The dotted line here in orange is basically when predictions match the observed experimental concentrations exactly. And the blue and red lines on each side is an under prediction and over prediction of factor 2. Generally, when it comes to dispersion validation, results are viewed as good if your predictions fall within a factor 2. Now in Phast 8.7.1 and earlier, you can see these predictions before the improvements basically in orange. And you see there's a tendency before we made these improvements to underpredict the concentrations for these buried pipeline CO2 releases. That was because we didn't really get the crater effects and importantly the gas blanket behavior done appropriately. So we didn't have any upwind spread of the cloud, for example, previously. But if you see here now at the green circles, this is the Phast 9.0, and all same was in Phast 8.9 when the new modeling was first introduced. You see that the predictions are very close to what was observed in the experiments. Similarly for COSHER 2, the second test, which was slightly lower wind speed at 1.9 meters per second, again, it's the same trend here that previously there was a bit of an underprediction going on in Phast, which was a concern. And we addressed that, and with the improved modeling, we see the good validation results again here in the green circles for Phast 8.9, 9.0 after we made those improvements. It's important to mention here, though, that this validation is based on 2 tests only. When more validation material, more experiments of buried pipeline release becomes available to us, we would have of course, liked to do further validation to get even more confidence in the modeling of buried pipeline releases for CO2. Right. Do you recognize these photos? What are we looking at here? Well, it's probably not a surprise if I tell you that we are looking at CO2 release, okay? You can clearly see the picture on the right. There's a pipeline. If you look carefully, it looks like this pipeline has ruptured. You can see dry ice around the pipeline here. But unlike what we've seen previously, this was not a controlled experiment. This was actually an accidental rupture of a 24-inch pipeline near Satartia, Mississippi in 2020. Now, it's important to mention that this accident, there was thankfully no loss of life, but several people were hospitalized, and I think about 200 people were evacuated. Now, the COSHER large-scale experiments I showed earlier was 8-inch. So here, the diameter in this accident of the pipeline was 3 times as big, which means that the area of the outflow is 9 times larger. So what we're talking about in terms of the amount of CO2 coming out initially following such an accident, you're basically talking about several thousand kilograms of CO2 coming into the atmosphere per second. So it's a serious amount of CO2 being released. And I'm not going to go into detail of anything on this incident. It has been covered extensively, but there's also a very comprehensive report from PHEMSA, which I have linked to here if you're interested in more detail. But one of the things I would mention is that one of the findings was that the operators' hazard assessment did not identify the scale of the areas that could be affected appropriately. So they underestimated what areas would be affected in case of an accident. And that sort of highlights the importance of good, robust hazard assessment. And with that, I'll go back to Phast. We are continuously trying and striving to improve our modeling when it comes to CO2 releases in Phast. And in the next version of Phast 9.1, we have some significant improvements that I will just quickly mention here. The liquid phase CO2 pipelines are handled by a submodel in Phast called PipeBreak. We have extended that model. We call it PipeBreak 2, and it will be released as part of Phast 9.1. And there are some crucial improvements for the release of liquid CO2. In particular, we now take into account the initial rapid depressurization regime, which is important for dense liquid CO2 releases. We also have better modeling for small holes when the aperture ratio is less than 20%. And there's an improved modeling of liquid CO2 densities as well, which gives you more accurate inventories. More details about this can be found. We had a presentation at the GCPS back in March this year on this model. But to summarize, the main impact is that we get more accurate liquid pipeline CO2 releases. It helps us avoid workarounds, and it gives us better predictions of the fluid inventories as well. I'll also mention some validation we did for the extended PipeBreak 2 model available in Phast 9.1. We compared against some experiments that was part of the JIP called CO2 pipe trans. Those releases were back in 2012, 2013. It was basically a 200-meter long pipe, 52 millimeter in diameter. Pressures were around 100 bar and the temperature varied from about 3 to 14 degrees Celsius. So again, dense phase liquid CO2. 8 releases were carried out from the end of the pipe, and the hole size was varied from 10 millimeter to 50 millimeter. Full validation of these experiments will be published, including dispersion validation. But what I can say is both discharge and dispersion validation in Phast shows good accuracy. Here, I will just show one example of that, namely the test 6, which was a small hole where the hole size was about 10 millimeters. So what you see here is the release duration on the horizontal axis and the total amount of CO2 released over time on the vertical axis. The red dashed line is the released CO2 as observed in the experiments. And in orange, you have the predictions from Phast 9.0 and earlier, before these pipe break 2 extensions. And you see here, there is an under prediction of the released CO2. But after we have made these improvements, you see the results in green. The upcoming Phast 9.1 is more conservative and more accurate for the amount of CO2 being released. The same test, we can also look at the pipe exit pressure. So what is the pressure at the exit where the pipe, where the release is happening? So this is obviously an important factor to get the correct flow rate as well. And here again, we see the time axis on the horizontal axis, but now that's on a logarithmic scale. I've made this logarithmic here so that it allows us to focus what happens in that very initial depressurization regime, so that the first tenths of seconds or the first fractions of seconds even. So again, the red dashed line here shows you the observed pressure at the pipe exit, while the orange line is the pipe exit predictions in Phast 9.0 and earlier. And what you see immediately here is that Phast 9.0 and earlier immediately drops the pressure down to the saturation pressure, around 40 bar in this case, and then does the modeling based on the saturation pressure. Whereas the extended pipe break 2 model coming up in Phast 9.1, shown in green, starts at the actual operating pressure of 100 bar, and then you have a drop of pressure, and you see this staggered, rapid drop of the pressure in the pipeline down to the saturation pressure. And what is happening here is quite complex behavior in this initial depressurization regime, where you have rarefaction waves traveling back and forth within your pipeline. And you can see how that is captured here by the extended pipe break 2 model. So all in all, again, good validation for the extended pipe break 2 model coming up in Phast 9.1. Now, finally, if you're interested in more information about Phast and CO2 modeling, we have our Knowledge Center online. We have some information there that is available for anybody, including some videos like this, which is how to model CO2 for buried pipelines, Phast and Safety. And then there is some content here that is only available to license holders, like a document that we issue with every release of Phast, which is basically a guidance document of how to best use Phast for modeling your carbon dioxide consequences. The last slide I've got on Phast here is just a select list of publication if you want to have more details about Phast CO2 modeling.
Hope you found the information useful in your work. See you next time, and goodbye for now.